video, we're going to continue our work with the chain rule. And so we're going to use the chain rule to compute some derivative formulas. First, remember our statement of the chain rule, which we proved and applied in a few real-world examples in the earlier videos. So the derivative of f composed g of x, that is the derivative of f of g of x, is f prime of g of x times g prime of x. Or the way I would like to think of it in the problems coming up is if we have a function that's more complicated and it doesn't fit one of our regular derivative shortcut rules, sometimes we can often substitute. Let part of it be u. And so this makes a function of u, f of u. Take the derivative of that with respect to u and you get f prime of u, but then the chain rule says you also have to multiply that by the derivative of the u with respect to x. In Leibniz notation, that's df over dx is df over du times du over dx. It's like the du's just sort of cancel out there. Now when we use the chain rule to compute derivative formulas, we're actually using the chain rule always in some form of substitution where we're applying it in conjunction with another rule. So it's always used in conjunction with another rule. For example, if we have the power rule and we do some substitution to get the power function, where we're taking the derivative with respect to x of u to the n power, where we've made some function, some substitution where u is an expression that's got x's in it, but n is a constant base. So if you can think of this function as being some complicated base but to a constant power, let u be the complicated base, and now you've got the derivative of the u to the n. Now the way this works is the power rule says that's n times u to the n minus 1 if I did the derivative with respect to u. But since the u and the x are different variables, I've made a substitution. I have to multiply this by the derivative of the u with respect to x. That's what the chain rule does. So here's an example that we could work out. Let's take the derivative of 3x squared plus 2 to the 67th power. Now if this was the second power instead of the 67th power, I might say, oh, let's just go ahead and just expand it out using FOIL. Maybe even the third power, work it out that way. But the 67th power, oh boy, talk about a mess. We could do it, at least in theory we could do it, but boy, that's going to be tedious. You're going to expand that out, it's going to have 68 terms. There's a lot of places to make a mistake. It's going to take us a long time to do it. It's tedious. It's time consuming, full of opportunities for mistakes. We don't want to do it that way. Luckily, the chain rule allows us a different approach that's going to make this a lot better. What we see is we have a constant power, but a more complicated base. Let u be that complicated base. Let u be 3x squared plus 2. And we have the derivative of u to the 67th. Now, I'm going to do this sort of two different ways to write this down. So follow along with the left, and then we're going to go back to seeing for the right. You know, in fact, I can just do this. I think I can zoom in where we basically just see what's on the left. Okay. So let's go through this one at a time. Okay, so the derivative of u to the 67th is 67 times u to the 66th. Remember, bring the power down as a coefficient, subtract 1 from the power. That's just the good old power rule. But since the u and the x are different, we need to apply the chain rule, which says we've got to multiply by the derivative of the u. Now I'm going to leave the first part the same for the moment. But I'm going to substitute in what the u is, 3x squared plus 2. Oh, we know how to do the derivative of that one. The derivative of 2 is 0. The derivative of this is just 6x, so we just get 6x there. And now I'm going to finally substitute back in the 3x squared here, 3x squared plus 2 for the u. So we have the u to the 66 is 3x squared plus 2 to the 66. The 6x times the 67 is 402x. So there we go. An alternative way of writing this down is going to be on the right. The nice thing about this is it's all in one set of equals here. But this has its advantages over here, is to work some of it out on the right, which makes the flow on the left just a little bit nicer. So again, here we let u be 3x squared plus 2, and we have the derivative of 3x squared plus 2 to the 67th is the derivative of u to the 67th. Again, that's 67 u to the 66 times the derivative of the u with respect to x. But rather than working that out here on the left, I'm going to work that part out on the right. So the derivative of u with respect to x is just 6x. So I can take that 6x and replace the whole du over dx by 6x. And again, I get the same answer. So it really doesn't matter which of those two ways we write it down. That's really boiling down to exactly the same steps. It's just a little bit two different formats for writing it down. Now, I will say this. After you get better and better at this, you might be able to do some or even all of this problem in your head. At this point, I've done so many derivatives, I could do this entire thing in my head and just write the answer down. But I strongly suggest at the beginning that you don't try to do that, that you try to actually physically write down what u is and write it down in one of these two formats that you see here showing all of your steps. Number one, I think it gives you a better understanding of what goes on. Number two, it's going to be easier and much less likely to make a mistake, particularly if you end up getting one like some of the ones we'll work at in a little bit where we have to do two substitutions, where you have the chain rule inside the chain rule, essentially the derivative of a composition of 3 or more functions. It gets a little more confusing then. It's going to be much better if you write things down. And next, if your instructor is going to be grading your work, if you do make a little mistake, but you show what you've done here, you're much more likely to get some partial credit if you, rather than just writing down an answer which is incorrect, which is very likely maybe get you no partial credit. So several reasons why I suggest that you do this. But actually, if you do get more and more practice at this, there are certainly ways to do some of this in your head. You absolutely cannot skip any of these steps, but some can be done in your head. Okay, now I'm going to give you 3 exercises for you to do. In these notes, you're going to notice that I typically have an example followed by some matched exercises, and then we're going to work out those on your own and then check them against my provided solutions in the notes and these videos. So here are 3 examples. I'd like you to write these down, or you could and work these out yourself. And you're going to pause the video, work them out, and then when you think you've got answers to all 3, then come back and we'll check them. Press pause now. All right, here's the first one, the derivative of 5x to the 4th plus 11 to the 64th. Well, that's not something that we have a rule for directly, but if we see that it's just a complicated base but a very simple constant power, we let u be the more complicated base, let u be 5x to the 4th plus 11, and now we just got the derivative of u to the 64th. Okay, that's just a power function. We know how to do that. Power function rule for derivatives says you bring the power down as a coefficient and subtract 1 to get the new from the old power to get the new power. So that's just 64 u to the 63rd. But the derivative is with respect to x, not u. So that means the chain rule comes into play, or the substitution rule. We did a substitution, so we have to use the substitution rule, which is called the chain rule. And so we take the derivative of the u and multiply it by that. Notice it is multiplication here, not addition, not substituted in, and so forth. So the derivative of the u is the derivative of this part here, which is 20x cubed. This u is the original. So notice for some things that we don't do. For example, we don't forget this du over dx. That's a common mistake. Just to do this part, plug in the value of u, which is 5x to the 4th plus 11 to the 63rd, and forget the du over dx. You can't forget that. The chain rule requires that. Another mistake I've seen students make a lot of times is instead of multiplying the two derivatives, which is the point of all the work that we've been doing on the previous couple of videos, is showing you that this is a product multiply derivatives. Okay, and so in spite of that, I've seen some people take either the take the 20x cubed and put it in place of the u. There's nothing that says you put u prime in here. U prime is out here. Okay, so anyway, this is multiplying these two things. The u to the 63rd is the 5x to the 4th plus 11 to the 63rd. And 64 times 20 is 1,280, and then the x cubed is there. So there's the answer right there. The next one's very similar. This time u is 3x to the 24th minus 8. And that's all to the 25th power. So that's the derivative of u to the 25th. So it's 25u to the 24th times the derivative of u. The derivative of u this time is 72x to the 23rd. And then 72 times 25 is 1,800. We got x to the 23rd, and we've got a u to the 24th, which is 3x to the 24th minus 8 to the 24th there. Now this next one here may look a little more complicated, but it's not really. The square root's just another way of writing the fraction power. So this is still a complicated, not real complicated, a complicated base, variable base to a constant power. So we just rewrite this as the square root of u, or u to the 1/2, where u is 16 minus 4x squared. And so the derivative here is 1/2 u to the negative 1/2 using the power rule. Bring the half down, subtract 1 from the power. 1/2 minus 1 is 1/2 minus 2/2, which is negative 1/2. But then again, we had to do a substitution. So the substitution rule, the chain rule, says that we must multiply by the derivative of the u. The derivative of the u here is negative 8x. Now we just substitute back in, and u is this here. So there it is in a nice format if you like power functions. But since we had radicals to start with, let's rewrite it back in radicals. This u to the negative 1/2 is u to the 1/2 in the denominator, so we can think of this as negative 4x over parentheses 16 minus 4x squared, close parentheses to 1/2, and that 1/2 power can be thought of as a square root. So probably if they gave it to us in this form, we should give it back to them in this form. Although from any of these last three lines are correct in terms of it being a complete derivative in terms of x. But this probably the last one is the nice one here. Negative 4x over the square root of 16 minus 4x squared. Here's a GeoGebra activity by Ravinder Kumar that works with these, just working with formulas. There's no visual illustration here. It's just working with formulas. You get to put in the inner function and the outer function, outer functions in terms of t instead of u. So he's doing a t substitution instead of a u substitution, same idea. And then this is what t is here, the inner function. And it will, once you put those in, it will figure out the correct formula here. Make sure this matches what you're trying to find the derivative of. Then you can step through, click these things one at a time to see these different pieces show up. But it sort of steps you through some of the parts here. So what I suggest you might want to do is to first work out several examples like this on your own, and then maybe run them through this for a little bit of a check. Okay, so I think that's going to conclude our initial work on deriving and explaining what's going on with the chain rule. And the chain rule, though, is going to be heavily combined with other rules as we go forward. It's really the chain rule that really opens up the class of functions that we can do derivatives for. So very important rule in derivatives is the chain rule.